Yes, I'm going to talk about dealing with covalent linkages. I'm going to give a brief recap of Astroke for dictionary generation, then talk about how to create links using CCP4 today, or at least in the new version of CCP4 7.1, and then I will talk about analysis of links in the PDB with a view to thinking about how we can improve links in the future. So to start off with, let's think about ligands. Well, protein-ligand complexes are important, we know that. They're important for structure-based design. So the production of accurate models is vital. If we want to infer biological conclusions or do calculation of interaction energies, protein-induced strain, and so forth. But the poor quality of many ligands in the PDB has been concerning. So this has been acknowledged in the literature in past years. So if we go to Cooper et al. In 2011, I'll just read out what we've got here. The quality of structures of small molecules in the PDB varies so widely that the data bank should not be considered as a reliable repository of structural information about these molecules. This is due to the difficulty in identifying and positioning ligands in medium or low resolution macromolecular crystal structures and the immaturity of the available validation tools. The poor quality of small molecule structures in the PDB hinders the derivation of general principles that govern small molecule protein interactions. Now that's quite a damning statement. This is saying not only that what we've got in the PDB is not very good, but also that a big part of the reason for it is the software that we're using. This led to the development of a number of tools and features to improve the way in which we're dealing with ligands, particularly in ligand description, fitting, analysis, and validation. So in the CCP4 world, we're talking about Astroke, Coot, Privateer. And indeed, in recent years, dealing with ligands has become much, much better. But what has been ignored is covalent links. These have been largely neglected until now. Indeed, it's quite hard to see how to do it. It's unintuitive, which means that from the user's point of view, it's difficult. How can we deal with this? So when talking about covalent links, we're talking about post-translational modifications, so glycosylations, phosphorylations, methylations. Could be talking about disulfide bridges. You might be interested in pyranose or N-link glycans. But in this framework, we're also talking about polymeric links. And so this is your links between peptides in the polypeptide chain, nucleotides and nucleic acid chains. And also links involving metals, but they're complicated due to issues with coordination and so forth. So we need to wait until we can generate good dictionaries for metals before thinking about links involving metals in too much detail. But in order to deal with links today, we typically need a CIF dictionary. So that will describe the link chemistry and geometry. That's a general dictionary that could be applied to multiple different instances. To specify a particular instance in your model, you need a link record in a PDB file or a struct.con record in the CIF file. Some link types already have descriptions in the monomer library, but as we will see later, they are relatively few. So ligand dictionary generation. Geometric restraints for proteins and nucleic acids are pre-tabulated. These are available in the monomer library. We're using them all the time. But for ligands, ligands are much more complicated. We need a source of prior information from somewhere. The common known structures, the ones that are commonly observed many, many times again, are dealt with automatically. So these already have pre-computed descriptions in the monomer library. However, new ligands require special treatment. They require a new description, a new CIF file, and that's where we bring in Astroke. Astroke's been around for a couple of years now. The idea was that the atom and bond classes in the CCP4 monomer library are too simple. So we need to do something better. So let's rewrite the CCP4 monomer library in light of the hundreds of thousands of small molecule crystal structures that are available that are solved at much higher resolution and not restrained in the same way as in macromolecular crystallography. Doing so will allow extended, more detailed atom typing, which should result in improved geometry dictionaries. And this is exactly what we've observed. So Astroke uses small molecule coordinate data, currently the crystallographic open database, primarily because it's free for us to use and distribute derived data. So how does Astroke work? Astroke introduces a new atom typing. Instead of having the first order atom typing that we were using before, we've now got a full second order and in some cases third order description. So let's consider, there we go. Let's consider the atom type of this hydrogen here. That's written down here. We've got a hydrogen that's, whose first neighbor is a carbon, whose neighbors are a hydrogen, hydrogen, and oxygen. Okay, that's pretty simple. But if we consider a different atom, we've got a much more complicated atom type. We've got a carbon that's a member of 2 5 and a 6-membered ring, whose neighbors are a carbon, a carbon, a carbon, a carbon, a hydrogen. And we've also got descriptions of their neighbors as well. So it gets quite complicated, but fortunately, we don't have to care about that because Astroke will deal with all of that automatically in the background. Astroke derives atom types from small molecule databases, and these are tabulated, distributed as parts of CCP4 for quick lookup so that we can all use them automatically. So what does Astroke actually do for you? It's got a few functionalities. First is the restraint dictionary generator. It uses the restraint tables to generate restraints for a given molecule, and it will output a CIF file. So it will give you your ligand dictionary that contains the bond lengths, angles, torsions, planes, karates, etc. Secondly, it's a conformer generator. So it will generate coordinates corresponding to one of the low energy conformers for this potential ligand, which may or may not be the one that's in your crystal. So the output of that would be a PDB file containing the coordinates. And third, and of most relevance to this talk, is link dictionary creation. So Astroke creates a description of a link between two components. Now, this is not just the link itself, but also it extends to the two individual compounds as well. So not only have we got to specify the bonds, angles, torsions, chirals, whatever else that Astroke thinks that we need to describe the link itself, but due to the chemistry changing, the individual compounds need to be modified as well. So this link dictionary will not only contain the link itself, but also modifications to the both components, which can be quite extensive. Such inputs, CIFs, could be from the CCP4 Monomer Library, so it could be that you've got a link between two components that are already known, or it could be that you've got your own custom CIF, you've got your own ligand that is covalently bound, and you need to create a link file for that. And the output of this is a CIF. So you've not only got a CIF file that corresponds to your ligand description, but we've now got another CIF file that describes the link and the changes that need to be applied to the original CIF files for the two compounds. So let's look at an example. Suppose we've got a cysteine here and we want to link it to this monomer here. We want to link the sulfur to this carbon here. The output will be something like this. So Astroke will create a single bond between these two, and it thinks about protonation. So it's, you can see that it's changed the hydrogens accordingly. But we might decide that one of the bonds in one of the, or both of the compounds wants to be different. So instead of this being a double, we want to change it to a single, in which case the output will be Astroke will think about the protonation, create a new dictionary that's got new bonds, angles, and everything, so that this geometry is hopefully sensible. The other thing that we might want to do is delete atoms from one of the compounds. So here we've got a traditional case of a covalent link between PLP and lysine. We want to link the carbon here, the C4A, to this NZ in the lysine. In doing so, we also want to delete the oxygen from the PLP, the O4A oxygen. So we tell Astroke to do that, and it will create a link between the two without the oxygen. It's deleted the oxygen, it's created a single bond between the two, it's thought about the protonation to put the correct hydrogens on. But in this case, we also need this to be a double bond, not a single bond, in which case you can see again it has removed the hydrogen that is now not necessary. So pragmatically, what else do we need? Well, we need a link record. Traditionally, we have got a link record in the PDB file that looks a bit like this to specify that a particular link, which in this case is called a NAG-ASN link, should be applied to these two particular residues in this instance of the model. But that's not enough. You can't just give it, you can just give it this link record. You can just put this link record into your PDB file, in which case it will go away to the Monomer library and try to do something with it. But you should also give it the CIF dictionary corresponding to this link that has been generated, say, with Astroke. So if you put this, in order to generate such a link record, you can do this in Coot by going to Extensions, Modeling, Make Link, click, and it will put the link record in your PDB file, but it's not going to create that CIF file for you. So this is not the way to do it. You can, however, now create Astroke links in Coot, which is a little bit harder to find. At the minute, it's in Extensions Modules CCP4, in which case you will get a new menu up at the top there, which will give you an interface a bit like this, which will allow you to do things like changing the order of the bonds, deleting atoms, changing the order of bonds between atoms, as I was describing before, that Astroke is able to do. This will not only put the link record in your PDB file, or the struct.com record in your mmcif file, but also create the CIF file for the link using Astroke. We can now also create Astroke links in CCP4i2 as of the, hopefully pretty soon, release of CCP4 7.1. So here in the ligands menu, we've now got this make covalent link with Astroke option. So let's see that in action, and let's go back to our lysine PLP example. So what we want to do is we want to delete the O4A from PLP, link the C4A to the NZ in lysine, and we want to make sure that this ends up being a double bond. Let's see how we can do this. I think I've got to. There we go. Okay, so we've got our density corresponding to the PLP. We can see up there is the lysine that we need to link it to. First thing we need to do is to get the PLP. So let's go to File, Get Monomer, type PLP in there, and it will go to the Monomer library and push PLP into the place. We then capital J to juggle fit, R to real space refine, and our PLP is fitted. Now what we need to do is to merge it into the model. So we do that, and then we can go to remove all the hydrogens from our ligand because we don't need those. Now there's our O4A atom that we need to delete. So let's do that. We go to delete atom and then click on the O4A. And we're now ready to create that link between the C4A in the PLP and the NZ in the lysine. Okay, so let's do this with CCP4i2. So we go to File, Save Mol to CCP4i2, exit out of Coot. There we go, we've now got our model saved. Let's follow off with a REFMAC job and see what happens if you just try to refine this without giving it a link record. So there's REFMAC running faster than it should do. I sped that up. It'd be nice if REFMAC was that fast. REFMAC's quite fast already there. Let's follow that with a Coot job. Let's run it and have a look what has happened to our model of this PLP. If we go to the ligand, you can see that REFMAC has refined it quite nicely, but for sure we do not have that link denoted by the dotted line between the two atoms that we want. So let's now close Coot, go to the CCP4i2 task menu, and go to the ligands section there, and go to make covalent link using Astroke, which is the new option that you'll see in CCP4 7.1. So you can either use a 3-letter code from the Monomer library or your own custom ligand description, but in this case we're going to use the 3-letter code for lysine, LYS, and it knows what atoms are in it because it has a look in the Monomer library. We want to link the NZ. We don't need to delete any atoms or change the order of any bonds in that one, but in the PLP, which is the second residue to link to, we want to choose the C4A atom. And this time we do need to delete an atom from it. Even though we've already done it in Coot, we need to tell the dictionary about it. We need to delete the O4A. And we also want to change the order of the bond between the atoms to be double. That would be enough to run it, but because we also want to apply it to the model, let's choose to search in this model for all of the potentially matching links and create link records corresponding to those. So we run the job. And when that's finished, CCP4MG will render a nice picture of the link to ligand, the link to compounds there. we can see that we've got a geometry dictionary as well as the model with our links applied as output from this task. So let's follow the refinements. We want to refine the model using this dictionary, noting that the link dictionary has automatically populated the interface, at which point we can run the task. And again, REFMAC's going nice and fast. And we can follow with Coot. Let's go to the area of interest. And sure enough, we can now see that our link has been created and used. We've now got those dotted lines. So at this point, we can perhaps have a look at the distance between these two atoms to check that it seems reasonable. 1.25, pretty close to the dictionary value. At this point, we can go into the ligand pane, switch on our isolated more property dots so we can look for clashes with the environment. We can have a look at the ligand distortions to see if the ligand's happy, and perhaps also display the environment distances and do whatever else analysis and validation you want to do for this ligand. Okay, so hopefully that it should be as straightforward as that to create links for ligands in future. I'm now going to move on to analysis of links in the PDB. So the objectives here are to assess the extent of the problems involving covalent linkages in the PDB, to facilitate remediation of the existing entries that may have problems, to inform and thus improve quality of future links, and increase the number of links included in the Monomer Library to make things easier for more people, so that we haven't got to go through the process of using Astroke to create new links again and again and again where it's not necessary. So the idea is to analyze covalent links in the PDB, to have a look at standard monomer library links, looking at the interatomic distance distributions. We want to have a look at links with explicit link records to indicate user intervention. We also want to identify missing links from the PDB. So we want to consider proximal atom pairs that may be covalently bound. And this will help to prioritize links to be added to the monomer library in future. So how are we actually doing this? We're using Gemi's link hunt. Credit goes to Martin Voida for that, who's been very useful in implementing things in Gemi that we need for this project. So we read the monomer library to get all of the standard known links. We then get the connectivity of known monomers from the PDB's chemical component dictionary, scan all of the PDB entries, and then find all possible links. So those in the monomer library, flag those with or without explicit link records specified, and search for potential unknown link types. So proximal atom pairs. So they may or may not actually want to be linked. So a few technical details. We're only considering PDB entries derived from X-ray diffraction data. We've got data deposited and successfully refined automatically with REFMAC. Occupancy is 1 in all atoms in the residues because we don't believe the ones with partial occupancies. We're ignoring polymeric links. The interatomic distance threshold used for detection is 1.5 times the dictionary value for a given atom pair. And we're only taking the closest atom pairs between residues in order to avoid excess false positive hits. So that means we're excluding atoms related by bond angles, torsions, etc. Okay, that's all of the details. Let's get to some results. So we ended up with 114,000 PDB entries being considered in this test set. And of those, there are 325,000 known links. There's a lot of links in the PDB. We're dealing with links a lot. So this, of course, is the non-polypeptide links. So that corresponds to, these are found in 38,000 of the PDB entries. That's 33% of the PDB entries out there. There are, fortunately, a lot fewer which don't have link records. So there's only 5,000 links found in 2,000 PDB entries, which is 2% of the total, which don't have link records for links which we know about in the monomer library. So they are worth looking at in a little bit more detail. But these comprise only 42 link types. They're mainly pyranoses, disulfide bridges, some involving metals, so iron, zinc. We could do better. We could include many more. But let's have a look at one of these particular examples. Let's have a look at zinc cysteine. here we're looking at box plots, which display the distribution of the bond lengths. If the link record has been specified in the PDB file, then we've got a very tight distribution. Yes, we've got a lot of outliers, but we've got a very tight distribution, which is good. If we do not have a link records, then as you would expect, the distribution is much more variable. And so we need to perhaps do something about this. We can improve these cases. Noting that the dictionary value agrees extremely well with that when you do use the link record. Now let's consider the proximal atom pairs where the link type is unknown. So it's not necessary, I'm using quotes for the link type because they're not necessarily linked, they're just proximal atoms that don't have a link entry in the monomer library. Of these, there are 925,000 found in 68,000 PDB files. That's 59% of the PDB. 609 of these links have a link record. So there are a lot of links out there that have got records that, for links that do not have a description in the monomer library. We could improve this, so we need to address this. And this is found in 42% of the PDB files in the PDB. There are 315, however, that don't have a link record, and it's these that may or may not be links. And it's these that we really want to analyze at this stage. They are found in 40% of the PDB files in the PDB. The 10 most common such link types are found here. So note that these are all metals and waters. So we've got water, magnesium, calcium, sodium, that contribute to a very large number of these links that we are finding. So this all adds up to the 925. But we can't really properly deal with metals yet. We've got to wait for Astroke to be able to deal with metals properly. So let's exclude metals, exclude waters, and consider what's left. So here's the top 5 hits. We've got cis, heme, arg, glue. And we can see just by having a look at this ranked list, well, we don't want to create a link between arg and glue, or arg and asp, but perhaps between cysteine and heme, lysine, PLP, BME and cis. We can look at these manually and say, yes, we do want to have links for these, and we can include them in the monomer library because they're popping up a lot. So let's make life easier for people in future. So this ranking prioritizes hits for manual consideration. So ranking could be improved by reducing false positive hit rate. For example, we decided that we don't want the arg glue links, and so here's one particular instance of why this is being popped up as a hit. We can see that this should not be here, this arg should not be here. This NH1 has a B factor that's 50% larger than all of the atoms in the environment, so we can utilize that information in order to exclude such cases so that they hopefully will end up much further down the ranked list. So the result of this is that new links are being added to the monomer library. We've already got descriptions for cis heme, PLP lys, BME cis, cis psych, and this will continue down. So this will iterate, and we'll get a new list of ranked hits as we include them, and we will iterate that process. More links will be added following inspection of the ranked list of potential links. And as I mentioned a second ago, the environmental B factor analysis may aid discrimination of false positive hits. So to summarize what I've been talking about, there are many missing links in the PDB, and we want to avoid this in future. Recent developments should improve the quality of future models, so we can now create better geometry dictionaries for links. We're updating the CCP4 Monomer Library with common links, and we've got improved user experience, which should facilitate link creation and usage in bespoke cases. But metals still require special consideration, and this is a focus area at the minute. Relevant tools in CCP4 include Astroke for the ligand dictionary, conformer and link generation, Coot for ligand fitting, model building and link creation, and REFMAC for refinement. And then the new task for creating covalent links is coming to I2 in CCP4 7.1. So here's our group. So people that really should be acknowledged and associated with this work, Gary, Faye, Paul, also Martin Voida for his efforts on putting things in GEMI that we need for the project. I should also mention John, Samir, Abik, and Robbie for useful testing and debugging things. And thanks to all the collaborations and for you to listening. Thank you.
Thank you, Rob. And let's see if we have any questions about links. Oh. Hi, Rob,
Hi.
and everybody else involved. It's really exciting that this has moved so far. I'm just wondering about your conundrum at the end, is how to flush these things out. With the approach that Kevin described this morning about doing some machine learning on that, on the parameters around valid and invalid links, help there to just throw things out.
Possibly. I think that sounds a bit overkill. I think the objective here is to make our life easier by not having too many things to look through. So it's just a case of prioritization.
But that's, I think, what Kevin was describing, is to just throw out the false positives, and then you're just left with the ones that you really care about.
Yeah, it's quite possible that I'll be able to do something that's, as opposed to us thinking about what the appropriate criteria is, we just let a machine decide what is correct and what isn't. That's an option. It's not something that's been thought about in the context of this work.
Okay, any other questions?
Hi, Rob. Here.
Hi.
Hi. Regarding metals, what would you recommend for refinement right now? Because we can build the links in Coot, like for example for a zinc finger. But what is best to do for refinement?
Okay, so yeah, that is something that we're working on. And unfortunately, at the minute, it does involve quite a lot of manual fudgery. I think the most important thing is to try and figure out what you believe the chemistry to be. So certainly sorting out the coordination, making decisions about what the most likely coordination will be is the first step. The external restraints syntax seems to be the way to go forward for the ionic links. So that's different to the covalent link metals. But if you're talking about creating restraints for ionically linked metals, then it's external restraints. At the minute, that involves doing it manually. We are working on creating automated solutions and hopefully making that much, much easier for users in future.
Thanks.
So, Rob, just almost a decade on from that commentary you cited at the beginning.
Yeah.
If you rerun the PDB with the new Astroke things, how much do you think we as a community can now counter that criticism credibly, or is there still a very large hole to be driven through by externals?
So I think links are not being dealt with particularly well, and metals are not. Hopefully, links in the very near future are going to be dealt with well, and hopefully, say next year, we might be in a similar position with metals. But with the PDB as a whole, are you talking about ligands though? So in that particular comment, they were talking about ligands, and I would say that yes.
No, I think the criticism was about all the small molecules.
So
and
small
Astroke now
molecules
exists, and so could you, if you took the, if you rewrite it, PDB redo, etc., do you end up with a much better quality ligand in the PDB as a whole that people can now seriously start doing what they said you can't?
I think it's hard to talk about automated refinement in that context because there are a number of different tools that are involved in that pipeline. So it's a model building and refinement process, and interweaved with that is validation.
I think that, sorry to interfere, I think that the ligands that are essentially correct but were refined with very poor restraints, we already see that those improve quite a bit. So we are definitely heading in the right direction. The problem with the PDB is that we need to get the rubbish out. And that is going to be much harder because you don't want to do that wrong.
Yeah, so it depends on the underlying modeling assumptions. So we can refine things better for sure, and hopefully we can help people to make some more sensible decisions. But if the modeling decisions are wrong, then what can you do? So the answer is yes, I think that today we're doing much better than 10 years ago.
Okay, we had a lot of discussion. Not a question still?
Hi, Robbie.
Hi.
Thank you for such a good talk. Your slide with the box plots.
Okay, shall I go back to it?
Yep. Right. So how tightly is that restrained? What do the ESDs look like for that?
So that's a good question. So I showed the dictionary value. I have not showed the SD associated with it. To be honest, I don't know what it is. That's a good question. It's using whatever is in the monomer library.
I think it's the default 0.002.
Yeah.
Will you take it or behind you? I thought Astroke would generate something taken from. So no.
Can I have a question? When can we expect, this isn't a question for you, this is the question for him over there. When can we expect the PDB, the WWPDB, to capture this information and give it to us?
Yes,
As in
please.
us, the consumers of the WWPDB, not the depositors.
Capture what information?
Oh, the restraint. What, John? Okay, sorry. What information? The ESD when the refinement was done on the metal complex.
Who was that question from?
What are the people from the PDB? Ah.
Once we start getting it in MMSIF, which is now happening, then we can do it.
Okay, very quickly because we're behind on schedule.
Yeah, just one comment that as the PDB, sort of globally, not just PDB, this is all of us, we are listening and we are watching what you're doing with links and when they're wrong. And we have corrected over the last year a very large number of entries which had completely incorrect links. So do keep bringing us feedback, and these kind of things are great. And we will fix things that are wrong, that we've got wrong.
Yeah, I think it's not a criticism, it's just identifying issues that need to be fixed. Like the main focus of this is looking forward and thinking about how we can create tools that will help things in future. But as part of doing so, for sure, we can go back and improve the quality of the existing models.
Just a very quick comment. A bad solution of metals would be better than no solution. And we've been asking that for 30 years.
Now, I think in the interest of time, we should really move on, but we have a lot of food for thought, and indeed, covalent linkages and metal binding sites are a very important point of moving forward in the future.